In our last lecture, we started talking about the concept of AC power or sinusoidal steady-state power, and we made a couple of important observations. The first one is that when you have a circuit driven by time-varying periodic signal, it is not instantaneous power that matters, but average power. The power that gets absorbed or delivered over one period of the signal is what is the meaningful measurement. The second observation that we made is that when you have a periodic time-varying signal driving a purely resistive load, the power absorbed by the load is not the average voltage squared divided by the resistance, or the average current squared times the resistance. Instead, the average power absorbed by the load is this more complicated expression given down here. From that, we came up with a new term called effective value, or RMS value. The effective value of a time-varying periodic signal is basically the DC equivalent of a voltage source that would yield the same average absorbed power as that AC signal. We saw that the effective value is given by this expression here. What you do is you have to square the signal, take its average over one period, then take the square root. In other words, we took the root mean square of the signal. So effective value and root mean square value mean the same thing. The final observation we made then is once we've established what effective or RMS value means, you can use that to determine the average power absorbed by a resistive load using the traditional V squared over R and I squared times R equations. The only difference, in the time-varying case, you don't use the magnitude squared, you use the RMS value squared. And that's what we saw on this page. We're now ready to take this a step further. What is the average power in a more general AC circuit? So now we're looking at the case where the impedance is not just a real resistance R, but it has a complex resistance R plus JX. In other words, you might have a circuit with both capacitors and inductors in addition to resistors. So let's look what happens here. So suppose you have an RLC circuit driven by a sinusoidal voltage signal, Vm cosine omega t plus phi sub v. The current is going to be some I sub m cosine omega t plus phi sub I. And in general, what you're going to see is that the current is not going to be in phase with the voltage. So they're not necessarily in phase. The question is, how is this going to affect the average power being generated or absorbed? So the first thing you might ask is the average power simply the average voltage times the average current? This actually is far from the truth. Absolutely not. We saw that that wasn't the case when you had a purely resistive load. It certainly is not the case when you have a load that has a resistance in addition with some sort of reactance. Likewise, you might ask, is the average power absorbed equal V effective squared over R? The answer here is no, unless, as we saw in the previous lecture, unless the load is purely real. The load is purely real, that equation does work, but it doesn't work where you have a more complex load that consists of resistors, capacitors, and inductors. So then we might say, is the average power the effective voltage times the effective current? Where effective voltage, of course, is the magnitude divided by the square root of 2, and the effective current is the magnitude divided by the square root of 2. Even here, the answer is not quite. We're getting closer to the right answer, but we're still not quite there. So let's determine what the average power absorbed by a load in an AC circuit is going to be. So imagine you have a voltage being applied to a general RLC load, and that's going to generate a current, once again at the same frequency as the voltage, but a different magnitude and a different phase. The instantaneous power is just the voltage times the current. But let's use a trig identity to simplify that a little bit. Cosine A times cosine of B is what? It's 1/2 times cosine of A plus B plus 1/2 times the cosine of A minus B. So this equation here, the Vm and the Im come outside the brackets, and there's a 2 in the denominator due to this. Then when you add the parts in parentheses, omega t plus phi sub v plus omega t plus phi sub I, we get 2 omega t plus phi sub v plus phi sub I. Then when you subtract omega t plus phi sub I from omega t plus phi sub v, you get this. And notice the omega t disappears. This part is a sinusoid at 2 times the frequency of the voltage. This term is a constant. So in other words, if you have a voltage and current as shown here, where they are out of phase, the instantaneous power, V of t times I of t, is going to be a sinusoid of twice the frequency, and it's going to have a DC offset, which is given by this term here with that also. So if that's the instantaneous power, the average power is just the middle point, which is just that there. So the average power absorbed in a general AC circuit is going to be what? It's Vm times Im over 2 times cosine of phi v minus phi I. And that gives us this equation here. It's a voltage magnitude times the current magnitude divided by 2 times the cosine of the difference between the voltage angle and the current angle. We can then do one more simplification, remembering that Vrms, or V effective, is just the magnitude divided by the square root of 2, and likewise Irms is just the current magnitude divided by the square root of 2. Instead of using the magnitudes in this expression, we can use the effective values in the expression, and notice there is no 2 in the denominator here. The 2 that was here is gone. So let's look at this equation a little bit more. We have an equation for the average power generated or absorbed is going to be the effective voltage, or the RMS voltage, times the effective current, times the cosine of the difference between the voltage and current angles. That cosine of the difference between the voltage and current angles, we're going to give a new term to. We're going to call it the power factor, or PF. Basically, this power factor is a measure of how much the voltage and current are going to cooperate with one another. Turns out that in an RLC circuit, the voltage phase and current phase can vary by as much as 90 degrees in a component or series of components. So phi v and phi sub I can vary by as much as 90 degrees. This means that the power factor can be anywhere between 0 when they're 90 degrees out of phase to 1 when the voltage and current are in phase. So let's see what happens when the power factor is 1. When the power factor is 1, we're saying that the voltage and current are in phase. That means that whenever the voltage is positive, the current is also positive, and whenever the voltage is negative, the current is negative. That means that when you multiply them together, you're always going to get a positive number, so the average power is going to be maximized. But what happens when the power factor is less than 1? In this situation, the voltage and current are not going to be in phase, So there are going to be some periods of time where the voltage and current are both positive. For example, between this point here and this point here, they're both positive. The voltage is positive, the current is positive. And there are going to be periods of time where they're both negative. For example, between that period of time and this period of time, they're both negative. But there are going to be other periods of time where one is going to be positive and one is negative, or the other one positive and one negative. So the fact that we now have some periods of time where the voltage and current are different sign, when you multiply them together, you get a negative number, and that's going to decrease the average power. So bottom line, when power factor is 1, the voltage and current are always cooperating with each other. That's going to maximize your power. When the voltage and current are not in phase, there will be some periods of time where they're cooperating with each other, and other periods of time where they're opposite in sign, and it's going to decrease the power. In fact, the worst case scenario is if the load is purely reactive. In other words, if you have no resistance at all, the voltage and current are 90 degrees out of phase and the power factor is 0, which means that the average power being absorbed is 0. And this makes sense because when we studied capacitors and inductors, we saw the capacitors and inductors don't absorb power. All that they do is they temporarily store energy. So this result we're seeing here with this equation agrees with observations we made earlier on with capacitors and inductors. Let's talk a little bit more about this power factor and this equation for the average power in the general impedance case. As we said before, power factor is a measure of the goodness with which the available power is being used by a load. A power factor that's close to 1 means the voltage and current are, for the most part, in phase, and they're both going to be positive or both going to be negative at the same time. And once again, the closer that power factor is to 1, the more in phase they are. The only way you can get a power factor of 1 is when you have a purely resistive load. So when you have a load that has some capacitors or inductors that cause the voltage and current to be out of phase, we get a power factor less than 1. And we introduce two more terms. A leading power factor is when the current angle leads the voltage angle. We call that a leading power factor, which is associated with capacitive loads. So this is what we see when we have an impedance that's going to be an R minus a JX. Likewise, when the voltage angle leads the current angle, or when the current angle is less than the voltage angle, we call that a lagging power factor. That is associated with inductive loads, which are going to have impedances that look like Z is equal to some R plus a positive reactance. Let's use this equation now to solve a problem. So let's look at this problem here. We are given a 60 Hz sinusoid, so a frequency of 60 times 2 pi radians per second. It is driving 3 different light bulbs, 2 incandescent light bulbs. Incandescent light bulbs can be modeled as purely resistive loads. In addition, there's a fluorescent light bulb given by this symbol here. Fluorescent light bulbs tend to have a complex impedance that has a resistive part and a positive reactive part. In other words, fluorescent light bulbs tend to have an inductive load. The magnitude of the voltage source that's driving these 3 resistors is square root of 2 times 120 volts. So the RMS voltage is that divided by square root of 2, or 120 volts RMS. In other words, you can think of this input as the signal coming out of a power outlet. So now let's use the equations we have for AC power to determine the power absorbed by the three loads and the power delivered by the source. So the power absorbed by the 192 ohm resistor is fairly simple. Because it is a purely real load, we can use the simplified equation VRMS squared over its resistance. The RMS voltage is 120 volts divided by 192 ohms. We see that first light bulb absorbs 75 watts. Likewise, the 240 ohm resistor, its average power is VRMS squared over its resistance. So 120 volts RMS squared over 240 ohms. You work out that math, it's 60 watts. So we see the first light bulb is a 75 watt light bulb. The second light bulb is a 60 watt light bulb. How about the power absorbed by the fluorescent bulb? This is more complicated. Because we have a complex impedance, we need to use the more general equation for finding its average power. So we need not only the voltage across the load, but we need the current through the load, and we need to compare the differences between the angles. So the current flowing through the fluorescent light bulb, let's label that as I sub FL phasor, is what? It's 120 at an angle of 0 volts RMS divided by the impedance 140 plus J 170 ohms. We get 0.545 at an angle of minus 50.5 amps. And because we're using the RMS value of the voltage, we get the RMS value for the current. If we use this value for the voltage, then the current would not be an RMS, it would be standard amplitude. So the power absorbed by the fluorescent bulb is what? It's V effective, or VRMS, that's 120, times IRMS, 0.545, times the cosine of the difference between the angles. Voltage angle was 0 degrees. Current angle was minus 50.5 degrees. You work out the math, you get 41.6 watts absorbed by the fluorescent bulb. The last thing we need to find is the power absorbed or supplied by the source. To do that, we need to know its current. So let's label this current as IS tilde. What we know is that IS tilde plus, let's call this I1 tilde, let's call this current I2 tilde, plus previously labeled I sub FL tilde. Sum of those is equal to 0. So IS tilde is what? It's negative I1 minus I2 minus IFL. So minus I1, the current through the 192 ohm resistor, is its voltage divided by its resistance. I2 is its voltage divided by its resistance. And the current through the fluorescent bulb we calculated previously, it's that. So when you subtract that, you get minus 0.545 at an angle of minus 50.5. You work out all that math, you get 1.53 at an angle of 164 degrees amps RMS. Once again, we know it's RMS because all of our voltages were RMS. So the power absorbed by the source is its voltage, 120 volts RMS, times its current, 1.53 amps RMS, times the cosine of the difference between its angles, 0 minus 164 degrees. You work out the math, you get minus 176.6 watts. This minus means what? It means that that source is supplying power, which you sort of knew had to be the case anyway because the sum of all the powers has to be 0. Sure enough, if you add up the power absorbed by the first light bulb, the power absorbed by the second light bulb, and the power absorbed by the fluorescent light bulb, they equal the power supplied by the source. That is conservation of power. We're now going to develop a slightly different way to come up with that power answer there. So we're going to skip this page here, we'll go back to that in a minute, and come up with a shortcut for finding the average power. These are based upon the fact that capacitors and inductors do not absorb power. They only temporarily store energy. Therefore, when calculating the average power absorbed by a load, you know that it's due only to the power absorbed by a resistor. So suppose you have a load here, and once again, this is a load that could consist of capacitors, inductors, and resistors. Suppose you know the voltage across it, and you know the current through it. What we know is that this part of the load is not going to absorb any power. It's only absorbed by this part. So you can use the standard equation I effective squared times R to get the average power. But notice we cannot use this equation here. The reason being, this I effective current is going through both the resistive and the reactive parts. But the voltage V effective is measured across the entire load. So if you have, let's say, a resistor and a capacitor in series, the voltage across a resistor is not this. That is why you cannot use that equation there, but you can use that equation. Likewise, if you knew the voltage magnitude across a load and knew the admittance, you could say that the average power was the effective voltage squared times the real part of the admittance or the conductance. Notice this equation reduces to that equation if B is 0. If B is 0, then G equals 1 over R, and the average power is the effective voltage squared divided by R, which is the equation we saw in the previous class. So we can now take this idea and this idea to solve for this power in this problem using these shortcuts. So using the shortcuts, using the first shortcut, we know that the power absorbed by the fluorescent load is what? It's its effective current squared times the real part of its resistance. But the effective current we saw here had a magnitude of 0.545. So it's 0.545 amps RMS squared times the resistance, 140 ohms. That is the real part of that resistance. You work out the math, you get 41.6 watts. Alternately, we could say that the power absorbed by the fluorescent load is V effective squared times G, where G is the real part of the admittance. The admittance Y for the fluorescent load is 1 over 140 plus J170. The admittance is a reciprocal of the impedance, and this becomes 2.89 times 10 to the minus 3 minus J 3.51 times 10 to the minus 3 Siemens. So this is our G, and then our B is the minus that. So PFL is the voltage squared times G. And you get the same answer. But what's important is that what you cannot say, V squared divided by the resistance. That does not work. Why? Because as we said here, this 120 volts is not the voltage across just the real part of that load, it's a voltage across the entire load. Let's do one more example. So here we have a circuit 10 cosine of 5t with a Thevenin impedance of 2 minus J2 driving a load of 3 plus J4 ohms. And we're asked to determine the average power consumed by the load using two different approaches. One is the more general power equation on page 12 of our slides, and two is using the shortcuts on page 17 of the slides. So first thing we need to do is determine the voltage across the load. It's voltage division. VL tilde is what? It's 3 plus J4 over 2 minus J2 plus 3 plus J4 times the phasor version of this is 10 at an angle of 0 volts. Notice this is not RMS. It's not given as RMS, so you assume that is the actual amplitude. So when you multiply that by 10 at an angle of 0 volts, you get 9.285 at an angle of 31.33 volts. To convert it to RMS, divide by the square root of 2. 9.285 over root 2 at an angle of 31.33 volts RMS. The current through the load from Ohm's law is the total voltage divided by the total resistance. That's 2 minus J2 plus 3 plus J4. That gives us 1.857 at an angle of minus 21.8 degrees amps, or 1.857 over root 2 at an angle of minus 21.8 degrees amps RMS. Once again, it's very important to remember whether your voltage and current phasors are RMS values or not RMS values, because you have that square root of 2 difference between them. So the power absorbed by the load is either V magnitude times I magnitude over 2 times the cosine of the difference between the angles, or VRMS times IRMS without the 2 times the cosine of the difference between the angles. Notice, because we have these two root 2's there, that gives us the same thing as doing that. So either way, we get 9.285 over root 2 times 1.857 over root 2 times cosine of the voltage angle minus the current angle. And once again, you got to be careful of these double negatives here. You work out the math, you get 5.17 watts. Other way to do it is using the equations on slide 17. So the power absorbed by the load, we could use I RMS squared times RL. I RMS squared is 1.857 over root 2 You square that. You multiply by just the real part of the load resistance. Guess what? You get the same answer. Or we could say that the power absorbed by the load is VRMS squared times the real part of the admittance of the load. So the admittance of the load, if ZL is 3 plus J4, YL, which is 1 over ZL, happens to be 0.12 minus J.16 Siemens. So this now equals 9.285 over the square root of 2 squared times 0.012. Guess what? You get 5.17 watts in each of the three cases. Bottom line, you do not need to use these shortcuts if you don't want to. You can always use the general equation given right here. With the general equation, one thing you want to be careful of, if your voltage and currents are not in RMS, you have the 2 in the denominator. If your voltage and currents are in RMS values, you do not have that 2 in the denominator. Now we're going to revisit the concept of maximum power transfer. However, now we're going to look at it in the AC case or sinusoidal steady state analysis case. If you recall, in the DC case, if you had a circuit replaced by its Thevenin equivalent, so it has a VOC and a Thevenin impedance or a Thevenin resistance of our Thevenin, and you want to attach a load RL and get maximum power absorbed by the load, there's a balance. Because if you try to make RL too large, you'll increase the voltage across it, but decrease the current through the load. Likewise, if you make RL too small, you'll make the current nice and large, but the voltage will be very small. And we saw that the power, which is voltage times current, is maximized when? When RL is equal to R Thevenin. In other words, maximum power transfer was a good balance between increasing the voltage across the load and increasing the current into the load. In the AC case, we're going to see that we have a similar but not identical situation. So if we replace the circuit by its AC Thevenin equivalent, so it has a Thevenin voltage VOC tilde, and a Thevenin impedance, Z Thevenin, which of course is composed of a real part, R Thevenin, plus imaginary part, J X Thevenin. What we're going to see is that to get maximum power transferred to the load ZL, you set the real part equal to the Thevenin resistance, seen by the load, and you set the imaginary part equal to the opposite of the Thevenin reactance seen by the load. The fact that we have this minus sign here basically means that we set ZL equal to Z Thevenin conjugate. So to summarize, in the AC case, you get maximum power transfer not when ZL is equal to Z Thevenin, but when ZL is equal to Z Thevenin conjugate. We call this impedance matching. Let's try to prove this very quickly, and then once we prove it, we'll do an example. So the way we're going to prove it is find an expression for the power absorbed by the load in terms of the Thevenin impedance and the load impedance, and then we're going to take partial derivatives with respect to both the real part of the load and the imaginary part and set both of them to 0. As you know, when you take a derivative and set it equal to 0, you basically find the local extremum, the local maxima, or the local minima. Okay, so let's look at the situation here. We know that the current through the load, IL phasor, is going to be VOC phasor over Z Thevenin plus ZL. Z Thevenin is equal to that. ZL is equal to that. And so the current through the load is given by this expression here. What we're going to do now is use this expression here to find an expression for the power absorbed by the load, and then take its derivative with respect to both XL and RL and set them equal to 0. So if you recall, the power absorbed by the load is what? It's 1/2 times the load resistance times the magnitude of its current. So let's see what that is. So if the power absorbed by the load is 1/2 times RL times the magnitude of the load current squared, we get 1/2 times RL times the magnitude of the numerator squared over the magnitude of the denominator squared. The denominator was a complex number. So to find its magnitude, you take the real part squared, you add the imaginary part squared, and take the square root. And of course, if you're squaring it, you don't have the square root, so you just have the real part squared plus the imaginary part squared. Now what we want to do is take the derivative of this load power with respect to XL first. Remember, when you take the derivative of a fraction, it's the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. So if you look at this expression here, XL shows up only in the denominator. So when you do the denominator times the derivative of the numerator, you get 0. Then you subtract, that's where this minus sign comes from, the numerator, which is RL times that, times the derivative of the denominator. Remember, we're talking about a partial derivative here with respect to XL, and so the partial derivative is going to be 2 times X Thevenin plus XL. The 2 cancels with that 2 in the denominator here, and we just get this. All of that is over the denominator squared. Finally, we set this equal to 0 and solve for XL. It's pretty easy to see that you simply set XL equal to minus X Thevenin. This solves the first half of the problem. Once you have that result, and you set XL equal to minus X Thevenin, the load power reduces to this expression here. Now we want to once again take the derivative, this time with respect to RL, and set it equal to 0. Now in this case, RL shows up in both the denominator and the numerator. So when we take the partial derivative, we're going to get the 1/2 times the denominator times the derivative of the numerator. The derivative of the numerator is just 1/2 VOC squared, minus the numerator, which is 1/2 RL VOC squared, divided by the derivative of the denominator, which is 2 times R Thevenin plus RL. So we're going to get this all over the denominator squared. The denominator is R Thevenin plus RL squared. You square that again, you get that to the 4th. And you set this whole expression equal to 0. Basically what we're saying now is that R Thevenin plus RL quantity squared has to equal 2 RL times R Thevenin plus RL. That's going to cancel with one of those. We get R Thevenin plus RL is equal to 2 RL. You solve for RL, you get RL is equal to R Thevenin. So our two sub-results from the first partial derivative, we set XL equal to minus X Thevenin. From the second partial derivative, we set RL equal to R Thevenin, and we get our final result that we set our load impedance equal to the conjugate of the Thevenin impedance. And that's the end of our proof. We can actually come up with that answer thinking logically as well. If you think about the situation here, where you have your Thevenin voltage phasor and the Thevenin impedance and a load impedance, ZL, you're going to have a current leaving the source, call it IS phasor. If you recall when we talked about power transfer before, we saw that power is maximized when the voltage and currents are in phase. That means that to get the maximum power out of this source VOC phasor, we want the load impedance seen by the source to be real. So you want a real impedance. If the impedance seen by the source is real, the voltage and current are in phase and they're always cooperating with each other. That means we want the imaginary part of the load impedance to cancel the imaginary part of the source impedance. That gives us a power factor of 1. That's the first part. Once we've accomplished that, this reverts back to the resistive case where you have just a completely real load, in which case we know that we set the load resistance equal to the Thevenin resistance, and that gives us the second part there. So what is the actual amount of power that's transferred when you have this maximum power transfer case? So we know that the power absorbed by the load is always 1/2 RL times the magnitude of the current squared. But the magnitude of the current squared is the magnitude of the voltage squared divided by the impedance squared. But the impedance is Z Thevenin plus ZL. Z Thevenin is R Thevenin plus JX Thevenin. ZL is R Thevenin minus JX Thevenin. These two cancel, we just get 2 R Thevenin. And so the load power is 1/2 R Thevenin times the magnitude of the voltage squared divided by 2 R Thevenin squared. So that becomes VOC magnitude squared over 8 R Thevenin. If we want to use RMS values rather than magnitudes, remember VOC RMS is just VOC magnitude divided by the square root of 2. So if you then use RMS values rather than magnitude values, you get a 4 here, and you might recognize this equation as the same as the DC maximum power transfer equation. So let's use this concept of maximum power transfer to solve this problem here. We're given a fairly simple circuit with the load consisting of a resistor and a capacitor, and we're asked two things. We're first asked to find the value of the resistor and the capacitor to yield maximum power transfer to the load, and then we're asked to find what that load power actually is. So the first thing we want to do is find the Thevenin equivalent circuit as seen by the load. So in other words, we want to replace this circuit by its AC equivalent, VOC phasor, and Z Thevenin. And then, of course, we set the load, ZL, equal to Z Thevenin conjugate. So what's VOC phasor? Well, the source is 24 at an angle of 0 volts. The 6 ohm and 3 ohm resistors are unchanged. The 4 millihenry inductor in the phasor domain becomes what? J omega L or J4 ohms. So VOC phasor is what? From voltage division, it's 3 over 3 plus 6 times 24 at an angle of 0. Notice that J4 has no effect on VOC. So it's 3 over 3 plus 6 times 24 at an angle of 0 volts, or 8 at an angle of 0 volts. So that's going to be our VOC. To find Z Thevenin, we basically set the voltage source equal to 0 and then find the Thevenin impedance looking into those terminals. From inspection, you can see that the Z Thevenin is 6 in parallel with 3 plus J4, or 2 plus J4 ohms. ZL then is just the conjugate of that, or 2 minus J4 ohms. So what do R and C have to be? Well, the resistor obviously is 2 ohms. For the capacitor, what do you want? We want minus J over omega C is equal to what? Minus J4. You solve for C, you get C is equal to 0.25 millifarads. So at this point, we solved the first part of this problem. We determined the value of R and C to give you maximum power transfer to the load. Basically, we've chosen R and C so that this current leaving the source is going to be in phase with VOC itself. The next thing we want to do now is to actually find what this power is. To find the load power, we actually can do that multiple ways. One way that always works is you use the power equation. You find the voltage across the load, you find the current through the load, and use that the power absorbed by the load is what? 1/2 times the magnitude of the voltage across the load times the magnitude of the current through the load times the cosine of the difference between their angles. So what's VL? VL from voltage division is what? 2 minus J4 over 2 plus J4 plus 2 minus J4 times 8 at an angle of 0 volts, or 8.944 at an angle of minus 63.44 degrees. What's the current through the load? From Ohm's law, the current through the load is 8 at an angle of 0 volts divided by the total impedance, which is 2 plus J4 plus 2 minus J4, or 2 at an angle of 0 amps. So the power absorbed by the load is 1/2. Remember, we need this 1/2 because we are not using RMS values here. Nowhere were we told that this voltage was an RMS voltage. So the power is 1/2 times 8.944 times 2 times the cosine of minus 63.44 degrees minus 0 degrees. You work out the math, it's 4 watts. An easier way to find the power, however, is to just utilize this equation right here. Because we have a maximum power transfer situation, the power absorbed by the load is just the open circuit voltage magnitude squared over 8R Thevenin. So PL is also VOC phasor squared over 8 times the real part of the Thevenin impedance. So you get 8 squared over 8 times 2, or 4 watts. So whether you use the general equation or the equation specifically for maximum power transfer, you get the same answer of 4 watts. One thing you want to remember, this equation here is only valid if you have maximum power transfer, whereas this equation is valid for any load situation. Have a good day.